Good afternoon, everyone. Welcome to the post-noon session of ITech program day 6. We have Professor Vikram Vishal with us, who will be delivering lecture on geological storage of carbon dioxide. He is an associate professor in Department of Earth Sciences in IIT Bombay. He is an expert on reservoir geomechanics in India, hydrodynamics of fluid flow in coal and shale, carbon sequestration for enhanced natural gas recovery in Indian unconventional hydrocarbon reservoirs. In recognition of his outstanding research contribution in the field of Earth System Sciences, the Ministry of Earth Sciences honored him with the Young Researcher Award in the field of Earth Science System in the year 2017. With this, I would request Professor Vikram Vishal to please start the lecture.
Yeah. Hi. Can you see me and hear me?
Yes, sir.
Yeah, great. Thank you so much. I'll try to share the screen here. Please confirm if that is visible. Is the screen visible?
Yes, sir.
Okay, great. So I'll turn off the camera just to save some bandwidth. Thank you so much for this invitation. I'm really happy to talk about opportunities and challenges in geologic carbon sequestration in India. So as said, my background, I'm basically a geologist and partly did PhD in civil engineering and my postdoc bit in chemical engineering. Truly interdisciplinary, background as the subject itself is geologic carbon sequestration. So yeah, going ahead with a brief background at IIT Bombay. So IIT Bombay has been a nodal center for various activities around CCUS, whether it is capture, utilization, storage, techno-economics, life cycle analysis, and also environmental impact assessment. These are all different dimensions of CCUS that are required, and collectively we have been engaged with different organizations to also and think tanks to come around policies related to CCUS. We have our faculty colleagues' participation in IPCC, in COPs, the Asia Clean Energy Forum organized by the Asian Development Bank, and also at the US Department of Energy's capacity building program, where I'm a faculty. That's again centered around carbon sequestration, that's called as REX program. With the IEA, so we have our colleagues and myself authoring and also reviewing the reports of the international energy agencies. And as we all understand, CCUS happens to be one of the important portfolios of climate change mitigation program. So India is also a key member of the Mission Innovation Initiative and European Act. So we have our group and other colleagues working under the initiatives of these two with the government of India. Most recently, we got a recognition by winning the X Prize Carbon Removal Student Competition led by the students, where Professor Arnab and myself were the mentors of the team. And it's heartening to know that some of the initiatives that we are taking here are getting global recognition. So we also co-authored the CCUS Roadmap of India that was released by DST 2 years ago. And currently, we are also working with the Ministry of Petroleum and Natural Gas to develop the 2030 Roadmap for CCUS in India. We also organized this conference in series. Last year we could not because of the pandemic. So essentially trying to focus on CCUS in India and how the development can take place. So with this background, I'd like to begin with my talk and some of the facts and figures which you all may have come across already several times during this course, and particularly today. India is one of the leading emitters of carbon dioxide. Of course, the gap with China and USA is much more. And when we also now talk about European Union as a single cluster, but overall, we are emitting somewhere around 3 gigatons of carbon dioxide every year, of nearly 38 to 40 gigatons that is emitted from globally. Now, we are projected to grow in the current size of economy from 2.9 trillion to 5 trillion USD and 10 trillion in 8 years from there. So what does that imply? So our energy requirements are going to grow. And since we are going to grow in our energy requirements, we'll use a large amount of fossil fuels because that's what the infrastructure and the availability of indigenous coal is supporting. So slowly we have to transition into reduction of emissions, but definitely our energy requirements are high and we have not yet reached the peak CO2 emission here. It's far. And in that process, we'll be burning more and more fossil fuels. Steel production, for example, is currently around 130, 140 million tons per year. It is expected to grow up to 300 million tons per year by 2030, by end of this decade. Cement production is projected to increase. The power generation capacities will increase. Of course, the share of fossil fuels in the power sector has drastically reduced since our commitments in COP21. And the crude oil import is also expected to be reduced, so up to 10% in due course. So there are ambitious targets for the country. The big ambition that we have set with the Prime Minister's announcement at COP26 in Glasgow earlier this month, India would achieve net zero emissions by 2070. So there are different pathways by which we can achieve net zero, of which let's say fuel efficiency or renewables are important parts of the portfolio. But CCS also looks like may account for a significant portion in India's efforts to achieve net zero emissions. So in the 1.5 degrees Celsius scenario, cumulative CO2 captured by 2060 is nearly 100 gigatons higher than under the 2 degrees Celsius scenario. So when we talk about the carbon budget in total, so it's somewhere around 400 gigatons is remaining. And at the current pace of 40 gigatons per year globally, we will come to that scenario in next 8 to 10 years itself. And it's not at what we are emitting right now. The projections say that we'll be on the trajectory to rise. So if there are no policy scenario, the red line that you're seeing here, the red graph here, you can see if there is no policy scenario, just talking about India, somewhere around 3 gigatons at present in 2020, 2021, we should be somewhere around 16 gigatons per year by the end of this century, India alone. So therefore, definitely we cannot go on this trajectory because we have to address our carbon emissions. And in that scenario, we have to talk about different, the pledge scenario, this is the blue one, and the limits 450 ppm, that is targeting, currently we are somewhere around 419 ppm of CO2 concentration in the atmosphere, and it has to limit itself to less than around 450 ppm. So for that scenario, we have to have extremely strong and stringent measures of carbon dioxide emissions, not just for India, but for the globe as a whole, so that we become like net zero and negative emissions in the years after that. So all in all, these are some of these points to trigger the conversation around CCUS and look at the scale that we are talking about in the order of gigatons of carbon capture and utilization storage. So when we talk about utilization to, let's say, green chemicals, it will definitely be driven by the market demands of those chemicals. For example, soda ash or urea or even methanol for that matter. So it is expected that India will remove 1 gigaton by end of this decade, and subsequently we have to upscale that. And so can it all happen by utilization to green chemicals or by afforestation or in the years down the line? So we need to look into those scenarios, and we cannot really omit the case of CCS in India. So we are working somewhere there. So CCUS is the way. So utilization, storage coupled together. So storage of CO2 from anthropogenic sources. So what do we do in CCUS projects? We have these large point sources of carbon dioxide emissions, and from there we capture the carbon dioxide and compress it, transport it to a fairly good distance where the sink space is, where wells are, and we sequester the captured carbon dioxide into the geological formations, hoping that it remains there for geological significant periods of time. So a detailed amount of studies has to go for each of the wing of CCUS. And also the bigger challenge here is the cost and the techno-economics of the whole process that also need to be understood. So what you're seeing on this left is the very popular picture from the Sleipner Basin, which is offshore of Norway, one of the biggest projects primarily on CO2 storage purpose. So this is the natural gas reservoir here, and around when the natural gas, that is methane, which is coming above, has somewhere around 8 to 9% of carbon dioxide in it. So this CO2 is separated from the natural gas. CO2 is separated and it is injected into a sedimentary formation, which is the Utsira formation. It's a saline aquifer, and in that aquifer we actually store this carbon dioxide in here. When we are injecting this carbon dioxide, there are several issues that need to be studied in detail. So when we plan for injection, we have to plan a couple of years in advance. We have to monitor the site. We want to ensure that the injected carbon dioxide do not move from there and go into other formations. So for that purpose, that is done. And this particular is a classic case of CO2 storage in the offshore of Norway, where CO2 plume has been injected and it's being monitored. So now the problem of global warming is more or less understood, and carbon sequestration as one of the methods is also understood. So there are a lot of technologies around the world. There are somewhere 17 large-scale CCS projects being implemented today. As of today, there are none in India as of now. So we need to really understand the reservoirs well if you want to target for geologic carbon storage. So we need to understand the way the gas will be trapped, the gas trapping mechanism. So I'll talk briefly about the mechanism in different types of reservoirs. What the three main questions are: when we inject, what is the ease of injection? So that is permeability. What is the integrity of this reservoir where we are injecting? So once we have injected, it should not blow out, it should not go through the conduits and fractures and get leaked somewhere. So we have to understand the integrity of the reservoir and the cap rock. And the cap rock is the impervious strata lying above the reservoir rock, which obstruct the flow of gas from the reservoir into other formations. And then the cumulative storage potential. So what is the maximum amount of gas that can get stored into that particular reservoir? So often we see that the CO2 as a gas molecule has a huge amount of volume, but when we go deeper into subsurface, naturally it will compress itself into the liquid or supercritical form because of the pressure temperature conditions. So most of the injection sites are deeper than 0.8 kilometer, that is 800 meters. At that pressure temperature conditions, the CO2 changes into a supercritical form. So the pressure exceeds 7.38 megapascals, and the temperature exceeds 31.1 degrees Celsius. In those conditions, we will have the liquid CO2 or gas CO2 convert into supercritical CO2. So that has totally different ways of interacting with the reservoir that needs to be studied. And you can see that clearly, if there is 100 volume of CO2, it becomes somewhere around 0.28 volume of CO2 in terms of volumetric comparison. So it becomes just like a whole building worth of CO2 becomes more like a tiny droplet when we go to that pressure. So therefore, there is a huge amount of potential for CO2 storage in the subsurface. So you must have listened to the other talks, so you know about the capture methods. Just to set the tone again, there are two primary ways of capturing. One is the direct air capture. So you have these sort of fans which pull the air, and what comes out of it through the reaction that is happening in between, primarily through the solutions that are there in place, is the capture of carbon dioxide. So the air that goes from the other end of the fan is devoid of any carbon dioxide. So, and then the carbon dioxide is captured and it is definitely transported to a certain place. It can be scrubbed out and used for different purposes. This is at a very, very low scale that it is working. And right now only few projects are in the world, but it is definitely very inspiring, because around 10 years ago, the cost of CO2 capture from direct was somewhere around $800 per ton. But down the line, because of so much of research that has happened, now it is understood to be somewhere around $100 per ton, which is very, very inspiring journey for direct air capture. And you may be aware of different projects in Canada, US, and UK and Switzerland that are talking about direct air capture. So the idea with the DAC is that we have these sort of fans installed everywhere, and we pull out the CO2 from the air. But for in the context of India, where we have emissions coming from large point of sources, it may not be of direct context right now. Although the concentration of CO2 in the atmosphere is more or less same, but the emissions that are happening in the Western world is largely from diffuse point sources of emissions, just like the vehicular emissions, but not so the case for India. So we may have to look for the point source capture to happen in India, and therefore there are different methods of doing this capture from the point source. So we have these emissions from power plants, steel industries, fertilizer industries, petroleum refineries, and steel plants. So there are different sectors from where the large point sources exist, and they are the ones which are releasing most amount of carbon dioxide from various processes in the country. So role of CCS in the 21st century world, it is one of the 14 grand challenges. So we understand there are primarily 14 grand challenges of the 21st century, more or less common to several countries, but this was by the National Academy of Sciences in the US. We have, for example, advanced health informatics is there, water is there, and one of them happens to be develop the carbon sequestration methods. So 5 of these 17 sustainable development goals are also addressed if we talk about CCUS, such as the climate action, clean energy, industry innovation, infrastructure, responsible consumption and production, and partnerships. So of the 17 SDGs, we can address 5 SDGs if we are talking about CCUS. Okay, more or less, it is understood it's a non-avoidable strategy for climate change mitigation, and by 2060, India could account for nearly 20% of the global CCS projects. So, as I said, we need to go from where we are at to a very high scale of CO2 capture and emission reductions parallelly. So, we have to see that this is the portfolio line. So, just talking about this 2 degrees Celsius scenario here, you are seeing of all the efforts that will take for the world to, by let's say by 2060, if we talk about in 2 degrees Celsius scenario, if we are talking about efficiency of fuel switching, nuclear and renewables, CCS would also be an important portfolio, part of the portfolio for CO2 emission reduction into the atmosphere, and as high as 14% in a 2 degrees Celsius scenario. And the study also says that it will be somewhere around 32% of all the efforts for meeting net zero by 2060 as a globe. So we are talking about extremely good numbers, but we have to come onto practical grounds and understand the challenges that are there in each of these processes. So I'll talk about these TRLs, the technology readiness levels, that is there worldwide. The TRL is there fairly understood globally. This compiled by Bui et al. In 2018. Most of these technologies, if we talk about from concept to proof of concept to lab prototype to pilot demonstration and commercial scale, most of the technologies in the world are, you can see on the TRL 6 to 9. That means really it is happening out there in the world, where different aspects of CCS are there in place, whether it is capture, transport, utilization, or storage. But when we talk about India, so we try to work this out for the Indian scenario. Most of these TRLs are in the TRL 3 and 4. So most of the researchers in their laboratories, they have been trying to verify the proof of concept or develop lab prototype. And it will need a lot of effort when we want to take it to the industry, and that can only happen through successful collaboration. And that is what the tone for CCUS right now, with primarily with the Prime Minister's announcement at COP26 for carbon emission reductions. So it will become imperative for the academic and the industrial world to come together and resolve this and advance the TRS from the low ones to the higher ones. So coming to the essentially to the topic of my talk today, geologic carbon sequestration. So what happens in this, as I mentioned, we capture the CO2 from wherever, primarily the large point sources. In recent case, it's also from the direct air capture. But large point sources, we separate the CO2 from the other gas like SOx, NOx, or even and then definitely the nitrogen. And we have highly concentrated carbon dioxide that is coming out of the scrubbed out, cleaned, pure CO2. So for geological storage, we may not need extremely pure CO2 as we require for chemical injection purposes, for chemical utility purposes. So it can be a little less pure, and that actually reduces the cost of capture. This purification itself is a very cost-effective, intensive process. So once we have these sort of CO2 that is captured, it is transported to the region where it is going to be injected in the subsurface. Now, this transport is also a different story. It can be transported through trucks, through rail, or through pipelines, and in some cases, it's also transported through ships. So we have to look into the cost economics. If it is very, very far, then the transport cost of compression and transportation can exceed the cost of capture and storage. So that is usually the case. It's very expensive to transport. So therefore, the distance of transport has to be monitored very carefully. And therefore, this is what we would like to address also as as IIT Bombay, as a center that we are working here. So CCUS has different dimensions. It can be used for pure storage, let's say in fractured rocks such as basalt formations where mineral carbonation takes place, or in the deep and mineable coal seams where it can be stored. Then there are saline aquifers. Let's say in the offshore of India, we know that there are aquifers. Even in onshore, we have aquifers where it can be stored, and we can store into the oil and gas reservoirs which have been depleted. So we know about these reservoirs since for years we have exploited these reservoirs. So we know about these reservoirs. They may be the prime targets for storage of carbon dioxide. Then we have enhanced oil recovery, where we use the carbon dioxide to enhance the oil recovery. And while the main aim is enhancing the oil recovery, but storage of CO2 is incidental. So nearly 30 to 40% of CO2 does not come out of the reservoir with the oil that is coming out. So it gets stored in the process. And once the EOR process is over, we can actually target these spaces for storage of carbon dioxide. Similarly, there's a process where we actually can derive additional amount of coal bed methane by the process of CO2 injection. So looking at the types of reservoirs, this is a pictorial representation for different types of reservoirs. So for example, we have this oil and gas reservoir system. In the first place, we see that CO2 is being injected here. It is driving together with water. It is driving here, and there's a miscible zone. So CO2 essentially mixes with the oil. It reduces the viscosity of oil. Sorry, and it just continues to flow towards the production well. So this oil mixed with CO2 comes outward. So otherwise, what is happening? The oil becomes too thick and the pressure of the reservoir has come down. Oil does not come out by the primary method of extraction of oil. So therefore, we have to look into the other methods. And this is how it looks like. So you have additional amount of oil that gets recovered and it is pulled out of the system. Now the CO2 that comes here, is a separator unit is there. So CO2 is separated from the oil is taken for purposes, and the same CO2 can again be recycled and used in this purpose. So we may recover nearly 60 to 70% of CO2 that was injected. So then the same is again reused. Again, we can have more amount of CO2 come in place. The second way is to go for enhanced coal bed methane recovery. So when we inject the carbon dioxide, captured carbon dioxide, it goes inside, and so the coal is essentially the coal that has carbon, and that has affinity for carbon dioxide over methane. So the moment it sees carbon dioxide, it picks up CO2 and it kicks out methane from its micropores. And if there are fractures to let that micropores travel to the production well, the methane will be driven out and it will go to the production well. So this is the process which is called as CO2 enhanced coal bed methane recovery. Coal is having methane. Any sort of coal, when you see, it has methane. It may have to different concentration, but methane is native to coal in the coalification process itself. So in seams or coal blocks which are highly gassy, that means it has huge amount of gas, we do extract methane by primary dewatering method. That is happening right now with most of the industries such as SR, Great Eastern, Reliance, who are producing coal bed methane mostly in the eastern part of the country. Eastern and east central part of the country. So but now if we provide them with large amount of carbon dioxide, it may also turn out that we can increase the amount of methane that is being produced, and that will lead to a large amount of CO2 storage as well as methane production. Then the third pathway is storage into the saline aquifers. That these are like, this sedimentary reservoir strata which have primarily saline water present into it. But here you can see that there are pore spaces, and the pore spaces may be fully saturated with brine or less saturated with brine. We have scope for injection of carbon dioxide here, so it may mineralize with the brine and the reservoir that is present, or it may remain as an additional fluid along with the brine. So just like the Utsira formation case where CO2 is being injected into the saline aquifers. Other than this, there is this basalt formation, which are basically iron magnesium silicates, and when we inject carbon dioxide, so it forms weak carbonic acid and it reacts, and so the SiO2 gets replaced, silica gets replaced, and it forms stable carbonate minerals, iron magnesium carbonates. You can also have a little bit of potassium and sodium carbonates being formed here. So these carbonate minerals are far more stable once they are formed. The challenge is to make sure that they are formed. So that is a challenge here primarily. However, the CarbFix project in 2015, they showed that nearly 95% of the injected carbon dioxide could convert into a carbonate rock in less than 2 years of time. So those sort of kinetics are also being worked at, and it's worth considering for India, because India has large amount of basalt deposits as well. The fifth and more philosophical way of storage could be to replace the methane from the methane hydrate deposits on the eastern coast of India, or in general as a science. So this CO2 can replace the methane that is present in the hydrate form. So it looks essentially, what you're looking at is sort of the fire ice, as it is called as. So fire ice, because this is essentially ice with water molecules or water cages storing large amount of methane into it. So when you trigger with the fire, it catches fire and burns because the methane here keeps on releasing itself. So that's also a theory, and it's practically demonstrated in the laboratory that CO2 can be substitute the methane that is present, and that will lead to storage of carbon dioxide and replacement of methane. But it's a from my understanding, it's a distant thing to happen, because right now we do not have commercial scale of methane production from hydrates anywhere in the world. They have only been at the pilot scale or demonstration phase, with the longest duration of around 60 days of methane hydrate production, and let alone CO2 injection for this purpose to happen. But as a one of these reservoir types, and also India is geologically rich in its reserves, so we have these methane hydrate deposits which can alone take care of the entire CO2 emissions, provided they are technically and commercially feasible. So talking about the worldwide status, there are some 19 large-scale CCS facilities in operation, and there are many in construction around the world. But then we don't have many as such in India, any CCS project happening. Nearly 300 million metric ton of carbon dioxide is already stored in different geological formations around the world, and theoretically speaking, somewhere around 27,000 gigatons of CO2 can be stored in different 600 sedimentary basins worldwide. Now, when we talk about emission reduction, we just want to store 2 to 5, or somewhere some estimates say 6 to 9 gigatons in 1.5 degree scenario. So we have huge potential for CO2 storage in the subsurface, and so that we can do this, transitions to net negative emissions and transitions to cleaner forms of energy. So this will provide the support that is needed for mitigation of CO2 emissions into the atmosphere. So status of CCS in India. So it's not a CCS project, but it's rather a CCUS project. All of them that I'm talking about. You may be aware of the Gandhar field project that ONGC is been trying to work on. So they're carrying out different studies. So we are one of the partners in the studies there with ONGC, and IOCL is capturing the carbon dioxide from the Koyali refinery nearby located, and this is expected that the CO2 that will be captured will be transported and brought to the Gandhar field, and it will be injected, and that will lead to enhancement of the oil production in the declining oil field. Similarly, MOU and studies have been carried out with Oil India Limited in the northeast part of the country, where flue stacks of hydrogen generation unit and gas turbine power plant at the Digboy refinery are being considered for enhancing the oil recovery in Nahar, Katia and Dikom oil fields in Assam. Then we have SR Oil and Gas Exploration Production Limited Company, primarily linked with CBM production from Raniganj coalfield and other places. And there they are also carrying out some of these feasibility assessment for pilot scale CO2 enhanced recovery. Coal India is also possibly doing, I'm not very sure, but some studies underway on CO2 storage in coal. And Ministry of Petroleum and Natural Gas in 2018 released this enhanced oil and gas recovery framework, where I happen to be one of the members of the committee, and this policy incentivizes EOR and IOR methods. And CO2 enhanced petroleum recovery is one of the first documentation on subsurface injection of carbon dioxide could be utilization for enhanced petroleum recovery. So that is something that also gives that impetus. So currently, the ministry have also constituted the upstream for carbon capture and storage committee task force, where we are looking at the 2030 roadmap for CCUS in India collectively. So the International Energy Agency in Paris, they released their Outlook 2021. So last year in Paris, before the lockdown, I happened to be there, where we reviewed some of the energy technology perspectives, and I understood that there is push around CCUS in the world, but with respect to India, it is not clear how we will go ahead with this scenario. So one of the major questions that came was the CO2 storage potential in India that has not been properly mapped. So this has been a major gap, I would say, from understanding our subsurface reservoirs. There was an earlier study by Holloway et al. 2008, primarily driven by IEA, GAG, and British Geological Survey, who did some assessment for storage capacities in India. But we wanted to have a more systematic assessment based on the information and data from each of the reservoir types. Similarly, the Global Carbon Capture and Storage Institute, that is in Australia, they worked out different storage capacities, collected the data, and for, let's say, for Australia, for US, Canada, China, Russia, they have all these numbers associated. What are these numbers? They are these CO2 storage resources in millions of tons of carbon dioxide that can be stored in the major oil and gas fields in these countries. However, you can see that the map of India remains blank. So there was no detailed assessment of the overall storage potential of CO2 in major oil and gas fields in the country. So coming from Paris, I took it on ourselves, and our group started working at it to work out the geological storage potential for carbon dioxide in India. And we looked at all the four major reservoir types, that is the depleted oil and gas reservoirs, saline aquifers, enhancement of coal bed methane by the coal seam sequestration, and also the Deccan basalts. So you can see in this map that I'm showing on the left-hand side, that we have mapped. So these are the bubbles indicating the potential capacity for CO2 storage. For example, for EOR, you can see we have the values somewhere from 0.5 to 2 gigatons. So theoretically, we have a complete capacity of 3.6 gigatons of CO2 storage in the category 1 basins. So they are the ones basins are the ones which are producing. And of late, Bengal basin has also moved into category 1 because we started producing since October 2020 from the Bengal basin. So from these basins, we see that their storage potential is very good for enhancing the oil recovery. Then we talk about the saline aquifers. So aquifers are again different strata above and below these oil-bearing strata, as well as just offshore of India, which may not have oil-bearing strata, but these aquifers are present in different basins. So we have this, 10 gigatons to 50 gigatons bubbles. You can see that I'm trying to show here. So all in all, we worked out the saline aquifer potential also. Then the basalt formation. So this block here, red block, and this red block here, showing the basalt potential, storage potential in Rajmahal traps in this part of the country, and Deccan basalts in this part of the country. So we have hundreds of gigatons CO2 storage potential, theoretically speaking, in these reservoirs. Then for coal bed methane, we have these different again these basins where coal bed methane is being produced, and we can enhance the production of coal bed methane by storing carbon dioxide. Now, when we talk about these capacities, we primarily try to work out the theoretical capacity and effective capacities. There are some relationship between them, and then what could be a viable capacity for it to bear. So when we talk about the matched capacity, that is exactly when we are doing the injection, how much it can go ahead and take finally. So this capacity essentially keeps on reducing when we go to the top of the pyramid. So when we talk theoretically, we worked out somewhere around 395 to 614 gigatons of CO2 storage capacity in India. So even if we take 10% of it, we will be somewhere around 40 to 60 gigatons of CO2 storage potential. So that may be a real scenario somewhere. But then even that is a good number when we talk about CO2 storage in the subsurface reservoirs in the country. So now I would try to move this talk towards the CO2 storage potential in the unconventional hydrocarbons systems, just as the shale gas, methane hydrates, and coal gas. Because so what does this pyramid indicate? Is the volume of oil and gas that is present in the conventional at the top of the pyramid, but also the ease of extraction from the conventional oil and gas reservoirs is high, because over the years we have been producing oil and gas from these systems. But if we go down the pyramid, definitely the volume of storage is extremely high. And then you have increasing volume, but then the needs to improve the technology and cost implications are high. With huge production of natural gas, for example, if you see this scenario from US, somewhere around, I think now US, so this is an old graph. I think now US is actually exporting shale gas from where it had started into early 2000, and it is exporting shale gas, and also CO2 emissions have come down drastically by using lower forms of hydrocarbons, that is methane. So therefore, this is something that is also interesting for Indian scenario to consider for enhancing the natural gas production, but also reducing CO2 emissions. So we need to do those studies also. So the questions that still remain to understand how much is the pore space. So where are the pore space where carbon dioxide can be injected and stored? What is the ease with which we can extract the natural gas, or we can inject the carbon dioxide? And collectively, the integrity of the system where CO2 is being stored. Under any circumstance, CO2 should not leak from its intended space, and for that, a detailed subsurface understanding and mapping is required. So very briefly about coal bed methane. So coal beds typically contain large amount of methane-rich gas that it absorbed onto the surface of coal. injected carbon dioxide efficiently displaces methane, as it has a greater affinity for towards the coal than methane. So we have prognosticated CBM reserves at somewhere around 92 trillion cubic feet, and therefore we have potential for enhancing the CBM recovery if we can pump in large amount of carbon dioxide. So what happens when CO2 is injected here? Coal picks up the carbon dioxide and it drives out methane. So from the case of primary recovery, it enhances the methane recovery, and therefore it can be stored there. There are different aspects in that we need to understand here, that there is a dual porosity. So essentially the gas is stored in the micropores and it has to flow through the conduits and it has to come out into the macropores. And macropores, that is the big fractures, and through that it has come to the production well. And then the coal is naturally fractured, but it is also a weak rock which you need to take care of the whole thing. Permeability gets affected because when we are injecting carbon dioxide, once the coal matrix reacts with carbon dioxide, or rather picks up carbon dioxide, it also swells. The matrix swells. Because of the swelling of the coal matrix, the permeability gets reduced because the fracture pathways are getting closed as the matrix blocks are expanding. So that becomes a challenge. So essentially, there's loss of injectivity that happens after that. Another challenge is that injected carbon dioxide changes from liquid to supercritical. So what are the lessons learned from subsurface injection of carbon dioxide in coal basins? Around the world, there have been different projects. One of the first ones was the San Juan basin in USA for enhancing CBM recovery. And then there were challenges, primarily again with loss of injectivity, and that affected the overall economics of the process. Nearly 50% of permeability was lost in the first year of injection, and therefore they had to create fractures and inject more CO2. And then subsequently, with the shale gas advancement, that project also did not really work for CBM production. Similar experiences were found in Japan, Poland, Canada, and other basins of USA, even in Australia. Nevertheless, because that's one of the methods of enhancing CBM recovery, it is still being considered for working out. And if not, definitely coal seams, once they are not considered for being extracted for energy, we can definitely target them for storage of carbon dioxide. Okay, let this go. Just this slide, maybe we can look at. This is again from a simulation from one of the projects that was done in US. So when we have primary recovery of carbon dioxide, we can have somewhere around 30 to 38% of primary recovery. When we talk about CO2 injection, we can recover nearly 94% of gas from the coal seams. So again, this is a theoretical aspect from laboratory experiment and simulations. But clearly, when we are leaving out 60 to 70% of gas, ideally we would want to exploit the reservoir and get more and more carbon dioxide, more and more coal bed methane out of it. And CO2 injection can be one of the methods of doing this injection. So we have carried out a series of experiments in our laboratory here. We have different facilities where we actually generate the subsurface condition in the lab. So it's a sort of a rock triaxial experiment. In this, we have this rock sample that is derived from either from drilling, or we get the coal blocks and we extract the core, which calls a core sample, and then we place it here in this thing. And then we have a pathway for fluid to flow inside of it. So we cover this cell into a complete environmental chamber. We apply hydrostatic confinement. We apply overburden pressure. Okay, and then we allow the fluid to flow, enter from one space and exit from the other space. So in that case, what we are studying is the flow storage attribute of this reservoir rock. And then subsequently that is used as an input for various numerical models. So through the numerical model, we try to study what is the rate at which methane can be produced with this amount of CO2 that is injected. So simply speaking, if you see this trajectory that is going somewhere like this here, it would have gone without a scenario of ECBMR, it would have followed a trajectory. Is there someone trying to speak? Okay, so if the trajectory would have followed somewhere like this, and in this case, because enhancement of recovery is happening, it goes into a trajectory like this. So these are simulations from some of the fields in India, which we tried to do. The idea here is that we can enhance the CBM recovery by doing carbon dioxide injection even in our reservoir types. Again, this is a big research problem from various dimensions, understanding the interaction of CO2 with coal, the thermodynamics of this whole process, the feasibility of CO2 migration in the subsurface, permeability, storage, deformation of the rock, and many aspects are there that we need to investigate before we can actually plan CO2 injection. Similarly, talking about shale gas, that has, how it has changed this in energy scenario, as I mentioned. But we need to understand the flow of, we can trigger some fractures here and there, and we get the gas come out of it. But we need to understand the flow that happens. It's Darcian, non-Darcian, slippage that happens, diffusion, sorption. So we have to understand the entire phenomenon of the storage and flow of gas that happens in the shale. So now CO2 theoretically can again be stored into these shale formations from where we are extracting the gas. It will take up, but then the challenges are there for shale gas production in the first place. Now with the US scenario, where they have actually produced so much of shale gas, these spaces that have been emptied by taking on methane can actually be locations for injection of carbon dioxide and storage. So again, from research point of view, large amount of work is being done globally to understand the potential of shale storage in shale gas. However, we need to understand how this fracturing happens and how this storage is happening. So I usually use this to explain to the students that this is how we can do. So you can see this is, we all have heard about this, what we call as horizontal drilling and hydraulic fracturing. These are the two technologies which have actually revolutionized the shale gas production from shale. See, I mean, most of the wells that are injected are vertical in nature, are purely vertical in nature, and from those vertical wells we cannot extract shale gas. So therefore we have to deviate our wells in the horizontal direction, so that it goes from one end to the other end. Now as the well is drilled, we actually inject this, in this case this is the ball and sleeve mechanism. So we inject these sort of perforated sleeves that go from one end of the horizontally drilled well to the other end, and we pump in high pressure fluid. And this high pressure fluid, when it is passing through, it goes through it, and at certain points it is checked. The ball that comes, it gets stuck to this point, and it pushes the remaining part, closes it, and this one part gets exposed to the pressure and it fractures. So because of this, the hydraulic fracturing that is triggered, you can see that an extremely impervious rock strata, which is highly porous but not pervious. So impervious but highly porous rock strata, which has large amount of gases present. So these fractures connect these pores to the horizontally drilled wells, and these wells then carry the gas to the production site. So this is how it happens. And now these pores which have been vacated can actually be locations for carbon dioxide storage. So, but then there are challenges, because as I said, this fluid that goes inside, primarily a water-based injection, and that is one of the biggest challenges when we talk about the shale gas production. Now, just to give you a sense here, see, often induced seismicity is linked with these fluid injection, which is also a fact. So same case will happen in case of carbon dioxide injections. So therefore, we need to identify the strata very, very carefully. But if you have this injection that is happening in a fairly well understood terrain, it will be okay. But if we are injecting this water in a space where there are pre-existing fractures that may be present, water can seep into the fractures on the left hand side. If you're seeing on the bottom side, it may reduce the overall effective stresses, which causes the fracturing of this block to happen. So along this fracture, when the one block slides on top of the other, seismicity is induced. So these cases can actually happen even for carbon dioxide injection if we trigger this CO2 induced seismicity, and therefore this needs to be understood in great details, and accordingly we need to characterize these locations for injection. So just to put to perspective, this graph that you're seeing here, the blue line on this is nothing but the overburden stress because of the geobaric gradient. And then what is happening here is the green line is the hydrostatic gradient. So it is typically 10 megapascals per kilometer, that rate it will be going. But for reservoirs which will have high amount of oil and gas present, this will be a higher one. So the pore pressure somewhere is high here. So somewhere like this. So when we are adding more CO2 here, the pore pressure will again increase. So when we increase this pore pressure, we do not want to exceed the least principal stress. If we exceed the least principal stress, then in that case, we'll be triggering fracturing, and that will be the scenario. So we have to operate in this window and this window and this window when we talk about CO2 injection in the subsurface. So those sort of studies need to be done in great details before the industries plan for it. So I'll skip this slide here, because in this I'm just trying to say that the scale that we need to understand is from nanopores. The gas storage that happens is that in the scale, 1 nanometer, less than that also. But when we are talking about these, in the reservoir scale, they are in kilometers wide. So from that fundamental, we have to expand it to the reservoir scale. That is a big challenge. Methane hydrants, as I did mention, has this mechanism for storage of carbon dioxide as well. India has a huge potential for gas hydrates, and on the eastern and primarily on the eastern side of the offshore of India, and on slightly also on the western offshore, but primarily on the eastern part. And we are working here to understand how methane can be produced, and also using CO2 injection, how we can produce the methane. So finally, the storage in the basalt formations. So basalts are high magnesium, iron, magnesium, calcium silicates that are present from the solidification of lava. These rocks, let's say in Deccan basalts, if you have visited Mumbai in and around, you will see these black colored rocks. They are primarily basalt, and the soil that coming from those weathering of those basalts. So naturally, CO2 has been fixed in the by weathering that happens in the of the silicates over geological time scale. Now, what we are trying to do is enhanced weathering, that is leading the minerals to turn into from silicates to carbonates by artificially putting the carbon dioxide into these formations. So because it is very much in its infant stage, and in India very limited work is done, but these formations may prove for optimal storage sites for CO2 emissions. So the good thing is that we have huge reserves, and around 300 gigatons of storage can alone happen in the basalt formations. So we work out the overall storage capacity through CO2 EOR. Why EOR? Because this is the low-hanging fruits in terms of carbon dioxide mitigation. So when we are injecting CO2, a portion of it can remain in the subsurface, while the remaining comes with the oil. So in that, slowly through this, EOR large-scale utilization, again in order of millions of tons of CO2 can be eliminated from the atmosphere by putting this into the subsurface. So we have worked for different category 1 basins, and we have worked out the overall CO2 storage capacity, and also added the Bengal basin now because it's a category 1 basin. And we have a systematic process that we need to know. So we collect a lot of data from the National Data Repository and apply different methodologies that have been developed around the world, and also specific to the Indian scenario. Then do a lot of whole spectrum of research that is needed in this. So finally towards the end, can we go beyond the routine and resolve the poromechanics of the unconventionals or even the reservoirs? So there is a host of techniques and technologies. Now the idea is to understand these reservoirs to greater detail, so that we have limited number of surprises. For example, geomechanics was not very integral part of petroleum industry since last for several decades, and until only last 2 decades it's become important. So because there have been events where we have had outburst of gases and oil that led to understanding that we do not understand the reservoirs better. So we cannot have those sort of surprises when we are artificially injecting carbon dioxide. So to have these mechanisms in place to understand this. So there are different methods that we are using here, such as small angle neutron scattering to understand these reservoir types, and then digital petrophysics. So we are doing this computed tomography of a rock block and trying to identify the pore spaces that are present. So you can see here that we have separated the matrix blocks, and that is a non-porous unit, and this is the porous part of the rock upon the analysis. And then we can also separate the green color, that is connected pores, and the red color, the non-connected pores. So we are trying to see how we can understand slice by slice these reservoir rocks. As I said, when we need to understand, we have to go from very fundamental units that compose the whole reservoir, and therefore we can go with these sort of assessments. So there are uncertainties that are associated, but as we slowly we analyze the existing data, we do some desktop studies, we go to the site, we have some monitoring data that happens for any oil and gas operations. When we go further and further, we are reducing the uncertainty by getting more and more understanding about the reservoir. And although the cumulative cost towards the end is high, but that's how it will be. We have to start from somewhere and go towards the point where we can have the understanding of the subsurface. So other issues that we need to take care are the environmental impacts, the safety issues, measuring of the CO2 that can be stored, monitoring of the CO2, MMV, or measuring monitoring, verification, accounting. So we need to ensure that the CO2 does not pose any threat to the ecosystem. There are different ways of doing that. We need to also ensure that there is no background CO2 emission that is happening from the biotic life that is there, that may give some erroneous results in terms of CO2 monitoring in the place. There are several socio-economic and political challenges also. Costs are very, very high right now. The whole challenge is to come up with methods that are low cost and can run at a low cost. And awareness and public acceptance is important, because we may not invite healthy, pleasant conversations from every end when we are trying to inject CO2 in their backyard. So that sort of an understanding is required. And pore space rights are different in different states in the United States, but in India, we need to see where exactly the pore space rights belong to, whether it's the mines, Ministry of Mines, or Ministry of Petroleum, or the owner of the land himself. You need to look into that. A detailed uncertainty and risk assessment is required. We do not have dedicated policies for sequestration, so that is required. Liability of the whole CO2 storage for long-term basis needs to be defined, and conformity with the international and national laws are also required to be in place. So to conclude with this talk, there is significant potential for exploring unconventional resources as well as the conventional resources for CO2 storage point of view. Now we have given the overall gas storage capacity for the country, as I mentioned, through the very systematic study of the methodology and the data that were in place. Now we need to understand site-specific gas storage capacity that can only happen through specific industry partners helping us with that. Prospects for CO2 enhanced oil recovery is definitely there, and the world is doing it. US has been doing it for past 50 years now, and definitely it has to have a business case because of which that they are doing it. Now India can actually show the pathway for CO2 mitigation and also meet the energy requirements through CO2 enhanced oil recovery. And although the problem of CO2 emissions is global, the solution for each of the reservoir is unique, and therefore for each reservoir, each field, from each basin to each field to each block to each layer by layer, we need to do a detailed investigation before we consider CO2 injection into the subsurface. All in all, we have to eliminate CO2 in orders of hundreds of gigatons overall. So it's in 1.5 degree scenario, we cannot afford to be eliminating all of the pathways or any of the pathways in our understanding to remove CO2 from the atmosphere. So as I would like to end, I just like, since there's a student community out here, or even the others, we need those ideas to be in place, how we can actually, exploit the subsurface for coming to understand the potential for geologic storage of carbon dioxide, at the same time to figure out the safety and security of the injected carbon dioxide, because that should not pose any threat to ecosystem and anything around. So this geologist Park Dickey, who said we seldom find much gas in an old place with an old idea. So sometimes when we think that we are running out of gas, we are actually running out of the ideas. And therefore this Time magazine featuring so many celebrities, but a chunk of shale rock gets featured because that was the rock that could power the world. And definitely the United States, it did significantly. And therefore it is important to see that how CCUS can also change the overall scenario for carbon dioxide mitigation for the country. So with this, I would like to end the talk here, and happy to take questions if any. Thank you.
Dear participants, if you have any query, you can ask it now.
If I may.
Yes, you can ask.
Thank you very much. Thank you for your presentation. And from my perspective, I think I've interacted with carbon sequestration for a bit of some time, but the perspective of which your presentation was very insightful and very broadening. More or less like carbon sequestration is the magic bullet to the problem of carbon emissions. And have a number of interests, but first I'll begin with the first one. Are we able to estimate how much has been sequenced for maybe past 5 years against established emissions? how much carbon has been sequenced underneath against how much has been emitted.
Yeah. Yeah. So thank you for the compliment. And yeah, as I understand, the how much of CO2 has been sequestered as against what is emitted. So this amount of sequestered is absolutely minuscule as compared to what we have emitted. As I said, we are emitting somewhere around 40 gigatons of CO2 every year globally. We have sequestered only 300 million metric tons so far. So the actual storage has been very, very less because of several reasons. Now that we have this after this COP 26 and the commitments that different countries have made, it is envisaged that CCUS will play a more role. So last decade was primarily the decade of developing the technology and understanding in terms of CCUS. Now that this is in place, we hope that this will be the decade where it will be actually translated into demonstration. Several countries around the world have showed promise, and in fact, there are many CCS facilities which are in advanced stages of construction. As I showed in the map there, it is expected by the end of 2040, we will have somewhere around 2,000 large-scale CCS facilities around the world that are primarily dedicated for carbon dioxide storage.
Yeah. And secondly, if I may, or should I wait?
Yeah, please go ahead.
Yes, on the same presentation that you showed on the numerous sites, CCS sites worldwide, are they government-driven, or the majority are able to give a reflection? The drivers on those sites, are they multinational sector, multinational companies? And if there's any specific names to which multinational companies is driving the construction of those sites?
Mm-hmm. Yeah, so there are different companies. Now there are startups also coming up, with this idea to capture and sequester CO2, and there are different companies which are involved. So it's these, any event. Let's say now the UK, the project that they are talking about, there are at least 5 companies who are coming together for deployment of CCUS. If I just talk about the Indian CO2 UR project, where ONGC first signed MOU with NTPC, and first later they signed MOU with IOCL, which is actually taking off right now. And MN Dastoor is the partner with IOCL to study the capture part of the study, and then the whole cycle basically afterwards also. And with the surface facilities that are required for going for subsurface storage has been conducted by ONGC with another company, I think Toyo Engineering also. So definitely, there are different companies, stakeholders in place who come together to do this sort of a study and deployment. So anywhere around the world, maybe 1 or 2 lead companies for each, but more or less they have a cohort of companies who come together to develop and deploy the CCS technologies.
Yeah, sure. Thank you very much.
Thank you.
Hello.
Hello. Yeah.
Thank you for your nice presentation, and it's very interesting. But my question is how we can collect, as we know that we have different source of this CO2. So how we can have a collecting mechanism for different sources to have to sequester underground?
Yeah.
What mechanism we can use?
Yeah, that's a good question. In fact, that is also being talked about. Let's say if we have several gigatons of CO2 storage capacity in a particular basin, or in order of hundreds of millions of tons, each source of CO2 may not be providing that much of CO2. So that's where your question comes. So how do we bring them together? So now the world is looking at the concept of hubs and clusters. So we have these CO2 sources, different hubs that come together, that share the common infrastructure of transportation of carbon dioxide and towards the site where it is going to be injected. So you can have the clusters of these storage sites also. But if I just talk about the Euclidean center of one of these basins, and then you have nearby areas, you have, let's say, a steel plant, you have a fertilizer industry, we have a power plant. So we can have all of them do the capture, and then the subsurface storage is large enough to accommodate large amount of CO2. So each one of them will have their own choice of method of capture, but definitely after the capturing, the transportation of CO2 can happen conveniently by the shared infrastructure in the hubs and clusters model.
Thank you very much. It is clear now.
Thank you. Yeah. if just one more thing which I usually show to the students is somewhere around subsurface injection. So often we have confusion that where it does go in the subsurface. Some time ago, I was asked what you're going to drill a bigger tank there. So now this group is fairly enlightened, but I would like to show that this is what we created. It looks like a numerical simulation. It was created by an intern student at IIT Bombay, and it's really nice to explain the policy, the principles of CO2 storage. So this is like a reservoir. CO2 is injected at the base. It's rising. It hits the cap rock, which is fairly impervious, and you can have high concentration of CO2 being formed here. So this is a stratigraphic or structural trapping, and this is a residual trapping or dissolution trapping.
So
But this
we
is
are
actually
not able to see your screen.
sorry. Okay, but I think we may have lost time also this. So
Okay.
yeah, you're not able to. Just a moment. Are you able to? So I'm just sharing full screen now.
Still not visible.
Can you see the screen now?
Not.
Not yet?
Yeah.
Yeah, okay. So I was talking about this particular model that was created by an intern student here at IIT Bombay. And,
the screen is not visible yet.
Not visible, yeah.
It's not visible?
No, sir.
Yeah, not visible.
Okay, I thought it was visible. Then just give me a moment again. So I'm sharing the full screen now. Are you able to see the screen now?
No, sir.
It's okay. Let it be. No problem. It's just trying to show something interesting. Anyway.
Sir, but you're trying to explain. I think you're trying to explain it vocally.
Yeah, but it was actually sure. But it's strange because I'm still sharing the same way that I did the before. Just a little. Let me just try one last time. Can you see the screen now?
No, sir.
No?
Okay. It says sharing is started. Actually, it may be processing.
Now?
No, sir.
It's really strange. This is exactly how I shared the rest of the presentation. But good that at least I could make for the rest. Let me try one last time now. Share screen. Main screen. So I'm sharing everything right away.
Yes, sir. It's visible now.
Now visible.
Finally, thank you. So this is something that we created for Science and Technology Communication, CCS primarily. So this is, looks like a very nice numerical model trying to explain that CO2 is injection at the base of the strata, and it rises up here, and it gets stored here, and then it just forms this plume here, and then it goes into this dissolution trapping. This is the cap rock, and you have high concentration of carbon dioxide that gives as the high ion. So it's easy to understand here, but then you have this. It's not a numerical model, it's a physical model. Basically, we want to show that we do not stimulate anything and everything to show this, but actually physically the processes are governed and how you can store the carbon dioxide. And similarly, we have a carbon capture model developed again by the intern here at ITB, where we are trying to show that CO2, which is flowing from the base, and we have a fan that is here, it comes out, and you can have this thing sprayed on the sides, which actually captures the carbon dioxide from the air. And what we have at the top is the free CO2 free air. So it's primarily used for essentially to educate the masses generally, for who are non-technical, but clearly to understand that there are physical principles that are engaged in the whole process of CCS. With this, I would like to end my talk. Yeah, thank you. Is there anything else? Or?
Thank you, sir, for very informative and insightful talk. I believe all participants will be taking this learning into their respective fields. We truly appreciate your time here with us today. Thank you so much, sir.
Thank you for the opportunity. I'm really happy to talk about it and any time further also. Thank you.